welcome. And I have the top of the hour, 11 o'clock Texas time when we're supposed to begin, but I still hear the beeping sound of people joining. It's kind of like when you make popcorn in the microwave. You know, you're supposed to wait until you hear the popping sound sort of slow down or stop. And we still have a lot of popping sounds, beeping sounds going on. So we'll give it another maybe 2 minutes and then we'll get going. Again, for everybody rolling in, welcome. I'm still hearing people rolling in, so we'll give it another minute or so, and then we'll get started. Okay, and I'm now showing 2 minutes past the hour, and the beeps had stopped, but now they started again. We'll maybe give it 1 more minute for people to roll in. Okay, I think we've got it. So we'll go ahead and get started. So, hi, welcome everybody. I'm Mike Riddle, president of NCAB America, and today we're going to be talking about ADSS and high electric fields. So let's get going here. By the way, do you see my cursor on the screen? Alexis, can you comment? Yes. Okay, you do. Good. All right, that'll help me later. Okie dokie, let's go. So this is a RCEP compliant presentation. That means that we've met their standards in order to be able to offer you continuing education credit if you want or need it. And they actually issue them, and we'll tell you what you need to do at the end of the presentation in order to actually get those continuing education credits. So the purpose, oh, and by the way, the fact that we're compliant with their standards doesn't mean that they endorse or agree with any of the content here. So purpose and learning objectives today are, we're going to learn about ADSS and high electric fields, why ADSS is sometimes used in such fields, what does that actually mean? We're going to talk about the problem of corona and dry band arcing and what you can do against each of those. We're going to explain the difference between space potential and an electric field. We're going to talk about why space potential analysis is done instead of actually analyzing the electric field. And we're going to show how you can use the results of space potential analysis when you're designing using ADSS cables. So our agenda for today, we've already done the introduction. I've covered the learning objectives. Again, at the end, we'll talk more about how to get your professional development hours. We'll do the actual presentation, and we will have questions and answers at the end. So please hold questions until the end. And I do ask that questions be related to this topic. You know, we certainly don't want to be talking about any business here. So let's get started. So first, just a quick reminder that ADSS is all dielectric self-supporting. So the dielectric part of this means absolutely no metal. So if I put armor on a cable, by definition, it is no longer an all dielectric cable. It's an armored cable. And then it's also self-supporting. And self-supporting means that it's designed to support its own weight. So a duct cable is not an ADSS because it's not designed to support its own weight. But an ADSS can be used in a duct. So you can go one way, but not the other way. And this webinar is going to assume that you're familiar with basic ADSS design concepts, and we covered them previously in our ADSS Engineering 101 webinar. And in that webinar, the following slide was there, which is now this slide, that ADSS standard polyethylene jacket, whether it's medium density polyethylene or high density polyethylene, is limited to not more than a 12 kV space potential. And we said this is because polyethylene degrades in a strong electric field, and that leads to tracking on the jacket. The jacket burns through, bad things happen, everybody has a bad day. And that for up to 12 kV space potential, you needed a track resistant jacket. And that the maximum that you could go in, and we'll see today, there's sort of not really sort of, there is an exception or a workaround, I should say, for this limit of 25 kV. So now we're going to fill in on that slide and add these tools to our engineering toolkit. So first up, why? Why would we want to put ADSS in a high electric field in the first place? And then, okay, well, what is a high electric field? And when we're discussing this, we'll also then understand the difference between an electric field and space potential. And when we've learned these concepts, we're going to be able to figure out where we can put an ADSS on a structure and what type of jacket we need on a structure given the operating voltage or the electric field on the line. And this is going to lead us to space potential analysis, and we're going to see how to do that quite easily. So first up, the why. Well, the why is simple because sometimes ADSS is the best or even the only solution. So there are some high voltage and ultra high voltage transmission lines that do not have a shield wire. So OPGW is not an immediate option. Here in the United States, there are parts of the Western United States, notably the Bonneville Power Administration area, where lightning is not a problem. And so that utility made a decision decades ago that they were going to build transmission lines without a shield wire. It wasn't necessary. So then when they wanted to get fiber optic on those lines, that was not available to them as a possibility. So they needed to do something else, which meant either they've got to retrofit those structures in order to be able to put a shield wire and therefore an OPGW on them, or do something completely different. In other parts of the country, it's because outages on transmission lines are very difficult, in some cases, maybe even impossible to get on today's power grid. Now, in theory, you might be able to install OPGW hot, so on an operating line, and that is doable, but there are significant, shall we say, issues and safety concerns in doing that. And so ADSS, in contrast, can generally be installed hot, and so it makes it an attractive option. And another reason to use ADSS is because of cost. ADSS, the cable is typically going to be on the order of half the cost of a comparable OPGW. So the what? So now we need to start understanding what an electric field is and compare and contrast that to what space potential is. And the definition of an electric field is a region in space around an electrically charged particle or an object in which an electric charge would experience a force on it. So the force means movement. And remember that movement implies both direction and direction implies further a distance. So we're going to see these concepts come up in just a moment. On an operating transmission line, that object in this definition up here is the conductors themselves. And the operating voltage is the source of this electrical charge that's pushing a charged particle. And what we learn is that that operating voltage on the line, we sometimes think of it as, the phase conductors are at, say, 138 kV, but that voltage is not really just on the conductor. It's actually in a field surrounding the conductor, and we'll show you that in a minute. So the field that we're talking about is the electric field. And to illustrate that, we're going to imagine a single conductor with a voltage of 1,000 volts on it above ground. So you're going to end up with something that looks like this. So this is our conductor with 1,000 volts. Here's our ground. So as we look at this more closely, what we're going to see is the black lines radiating out from the conductor are the electric field lines. And then we could then find that at any point in space, there is a space potential. And then we could find that if the black lines are the electric field and we measure them in volts per some unit of distance, those space potential points are just a volt. And we could then draw lines where this point is at the same potential as this point, and that's what allows us to draw these rings. And we call them lines of equal potential or equipotential. To look at this more closely, we also see that the ground beneath our conductor is distorting the field below it compared to what we see above it. So if we just arbitrarily want to see, okay, if the voltage here is at 1,000, where is it? And we know at ground, by definition, it's 0. Where is the halfway point? And beneath the conductor, we would find this point here, and we would see a certain distance over that for that 500 volt change. But above the conductor, there's nothing to ground the field, to drive it to 0, or you could say distort it. So it just radiates in theory to infinity. But because there's nothing driving it to 0, the drop in voltage takes more distance. And so for that same 500 volt change, it takes a greater distance than the distance it took for the 500 volt drop below the conductor. And because of that, because this distance here is greater than this distance here, we'd say that 500 volt change over the distance here, this is a bigger number, so this number is going to be less than this number. So we say that the field from the conductor to ground is higher or stronger or more intense than the field above the conductor, because this number is bigger. Okay, I think that's clear. Keep going. So now we know that the space potential is that electric force at any one point in space. And because it's at just a point, there's no direction and no distance. And it becomes helpful to work with those equipotential lines because they're all at the same potential. The electric field, in contrast, does have a direction, and it does change over distance. Its strength or its intensity is not uniform. Again, look at the illustration. So here, the field is more intense than the field is here, for example. The common unit of measurement that we use is kilovolts per meter, but of course it could be something else, kilovolts per foot or whatever. And when we call it a high electric field, it's just a relative term. It's convenient for us to think about a high field as the point at which real world problems start to occur. But the challenge there is the fact that there's a big range on when that is, depending upon basically what's actually going on in the situation. So 500 kV per meter to 3,500 kV per meter, somewhere in that range is when you're going to have ionization of the air and bad things happen. So we talked about just a single conductor. And as we know, actual transmission lines have more than one conductor. So what happens to the field then? And the answer is that each conductor is radiating its own field that interacts with the field from the other two. And they're also interacting with things in the environment around them, specifically the structure itself. And you see that in this picture here. So the the fact that we have three phases on a transmission line creates a lot of additional complexity, and it's a classic good news, bad news type situation. The bad news is because it's so complex, do we have to do 3D modeling of the electric field along a transmission line in order to properly understand where we can safely put ADSS field? That would be really difficult because on actual transmission line, the geometry is changing along the span because of the conductor sagging, and they change even more because of changes in temperature in the environment and changes due to the current flow on the conductors. When current flow is going through the phase conductors, they'll tend to heat up. The heating makes them elongate, which means they sag more, which is changing our geometry. And therefore, it really complicates any attempt to model them. But the good news is that it turns out that the Maxwell's equations, when you look at things, we catch a break. It turns out that at the structure, the field is going to be along the axis of the line. And if that line is a cable, that's actually going to prove to be helpful to us. And I'll show you that in a minute. By midspan, though, the field is orthogonal to the line of or the axis of the line. And again, I'll explain in the detail why that is actually a benefit to us in a minute. So, and then the structure is going to be grounding the field in its immediate vicinity. And hardware that has metal in it is going to do the same thing. And these will be important to understand what's going on here as we continue through our journey today. So why does this change? Why is it positive? It means that electric field problems are likely limited to the immediate vicinity of the structures. So we can focus our attention there. We don't have to worry about what's going on at midspan. And then that means that we can use two-dimensional analysis instead of three-dimensional analysis, focusing that two-dimensional analysis specifically at the structure. And then in turn, that's going to allow us to use space potential as a stand-in for the electric field's intensity. So it becomes sort of like a surrogate, and we don't have to do this much more complex 3D modeling. And then, well, why is that? Well, let me see. I'd like to go here. Sorry for this, because we're going to come in a moment to dry band arcing. And the reason the field direction becomes important is that at the structure, we're going to see the field is along the line of the cable with a direct voltage drop in one direction towards the structure. So it's positive out here, and then by the time we're at the structure, it's at zero. So remember, electric current tends to flow from a positive to a negative or a zero. But at midspan, if the field is orthogonal to the axis of the cable, there's nowhere really for it to go. That's why that's important. So come back. So we talked about problems. The problems are two for certain and sometimes a third, and I'll come back to microsparking at the end of this presentation. So the two that are definite are corona and dry band arcing. We'll talk about these in a moment. And by the way, I want to go ahead and acknowledge Monty Tiomanen is a retired engineer from Bonneville Power Administration. He frequently attends these webinars, but couldn't be here today. And he's the source of many of the pictures, and he's the one who basically educated me. So I'd like to thank him for that. So corona is an electrical discharge on ADSS that occurs at the tips of the armor rods that are used in the suspension clamps and dead ends. The rods are acting to distort the electric field by forcing it to zero. So in effect, this causes the field intensity to intensify close to the rods beyond the ionization limit of the air. And so that means you get charge leaking off the tips into the air, and that's kind of like a plasma, and it's very hot, and that discharge burns through or damages the jacket. And that will ultimately cause catastrophic mechanical failure, which is a fancy way of saying that the cable will burn through and fall down and everybody has a bad day. So I don't have pictures of corona on ADSS because you'd have to be there when it's happening, but this is corona occurring on corona rings, which it shouldn't occur on. So why is it here? But you see this kind of purplish blue glow, it's corona. And these are supposed to be preventing that. So why is it happening? Well, they may not be designed correctly. That's possible. But basically, when things get sharp or pointy is when you get concentrated electric field and you can exceed the ionization limit of the air, and that's when you're going to get corona discharge like this. So either these are not designed correctly or maybe they weren't made correctly. Or it's also possible that they could have like salt spray on them or something that's accumulated and having a similar effect as a sharp edge would. So I've seen a similar thing happen on UHV spacer dampers that I knew were not made correctly. Long story for another day, I suppose. On ADSS, though, I can show you a picture of when it has happened and what it's done to the cable. So here you see an ADSS cable, and you see the armor rods from a suspension clamp or possibly a dead end, and you can see that they were not installed evenly. And all it took was this one rod to be poking out a little bit to force the field to zero and thereby distort it and intensify it in this immediate area. And you got the corona discharge. You can see it's damaged the tip of the wire a little bit, and it's burned through the cable jacket. So this cable was going to fail mechanically real darn soon. But there is a solution to that, and it's corona coils. Well-made, well-designed, and well-made corona coils will grade or smooth the electric field so that its intensity stays below the ionization limit of the air. And so therefore you won't get corona discharge. And these little wiggly things, that's corona coils. There is another possibility. You could have installation crews install the rods perfectly evenly, and if the tips were nicely rounded, you won't get corona either. So, if the rods had been nicely rounded, this one looks reasonably well rounded, but if it had been installed where everything was nice and flush, you might not have gotten corona there. But that's asking a lot in the real world, so I think corona coils are the better solution. So we've talked about corona. Now we're going to talk about dry band arcing. And an analogy for dry band arcing on ADSS is tracking that occurs on insulators. There are three ingredients. They all have to be present. You have to have a high electric field. You have to have contamination on the jacket, pollution, salt water, something like that. And you have to have a little bit of moisture. Um, then here's how these work together. So the cable gets wet. The contamination on it makes its surface a little bit conductive. The capacitive coupling between the cable and the conductors, in other words, the electric field, induce a current flow. The current causes the water to heat up a little bit and it dries, but it doesn't dry evenly. So you get small dry bands on the cable surface. Those bands stop the current. However, then they begin to act like a capacitor. So you get charge build up on one side, uh, on the midspan side of these bands relative to the structure. And then that creates a voltage across those dry spots. When you get enough charge built up across a dry band, you ionize the air and you get an arc across that band. So basically, you've made a capacitor. Then the arc itself uh, extends the dry band and uh, eventually dries the cable enough so that it stops. But by that point, the arc itself has been damaging the jacket of the cable, and you get this tracking damage. And that's illustrated here. Again, don't have pictures of it actually occurring, but I can illustrate it with this sketch. So you've got your cable here, it's wet here, wet over here, but it's dried a little bit here in the middle. Charge builds up on the midspan side of this dry area. When it gets high, enough charge is accumulated, it arcs across and damages the cable in the process. And here's what it looks like after. So I don't know on your screen if you can see it very clearly, but by the way, these slides are available to you after today's presentation, and then you would be able to see this picture perhaps more clearly, and you can see the little pattern that's been burned into this cable, and that's the consequence of dry band arcing. Eventually, it gets bad enough, it can burn through the jacket, and then again, bad things happen and the cable will ultimately fail mechanically. So how do you solve that? Well, that's why tracking resistant jackets were invented. So today, most companies that make ADSS offer both a standard polyethylene jacket and a tracking resistant jacket. The materials that are used for this tracking resistant type jacket will vary, but polyethylene with anti-tracking additives is a common solution and it works quite well. So then this leads to the question, how do you know if dry band arcing could be a problem and that you should use a tracking resistant jacket? And that's a great question. And that's what our space potential analysis is going to be for. So recall that we talked about the where and which type of cable to use from some minutes ago. And our space potential analysis is going to enable us to determine where uh, the voltage is high enough to be of concern. And from that, we're going to know where we can safely use a standard polyethylene jacket and where we need to use a tracking resistant jacket. And then which cable to use follows directly from what you've learned here. So To go ahead and orient you, and this is actually goes back to a very early slide, standard polyethylene jacket is good for up to 12 kV space potential. And from 12 kV to 25 kV, we need a tracking resistant jacket along with the corona coils. Um, the cable alone can withstand up to 25 kV. We will show you a workaround for that as we get towards the end of this presentation. Now, do we have to do space potential analysis on every single line? The answer is no. It works out that some operating voltages are of more concern than others because the higher the operating voltage, the higher the electric field is going to be, all else being equal. So in general, we can say that up to an operating voltage of 35 kV, you're not going to have a danger of tracking. And I do mean phase to phase voltages here. I probably should have made that clearer. From 35 kV to 138 kV, it's not likely that you're going to have a problem. I mean, you have to be trying hard and mounting your ADSS really close to a phase conductor for you to have a problem. But space potential analysis is available to confirm that a standard jacket is okay. From 138 kV to 230 kV, really I should say 200 kV, for those outside the United States, it could be a danger, and so you ought to check. And so I would characterize space potential analysis as highly recommended, as I write here. Above really 200 kV, it's absolutely a danger, and you absolutely need to use a tracking resistant jacket and corona coils. And you need to run the space potential analysis just to make sure that you're not exceeding that 25 kV limit for your track resistant cable. So how can you do that space potential analysis? Well, you've got at least two tools available for you. There are Excel workbooks that exist for doing space potential analysis. It's a lot of math, um, but it's pretty straightforward. And I mentioned Monty Tiomanen earlier in the presentation, and he put together such a spreadsheet for BPA. And if you're an American citizen, because BPA is a federal entity, you can request a copy from them. And then Monty would even be available to help you use it. So that's one possibility. The other possibility is that in CAB, we've put together a tool that we call ACES Spot. So this is our advanced cable engineering system, space potential analysis tool. And we'll show you that later. But they both are doing the same thing. You'll get the same results using one versus the other. So how does it work? In concept, regardless of the tool that you're using, you have to have your basic line geometry. So here's a 345 kV H frame transmission line. You have to plot out the Cartesian coordinates for where everything is. So in here, I've got the three phases as 1, 2, 3, and I've plotted their points. And then the two shield wires are important too. I've assumed an OPGW diameter, OPGW up here, and just a standard 3/8 inch EHS cable over here. And the phases themselves are bundles of two 795 Drake spaced at 18 inches. So then once you've put in your geometry and the operating voltage information, you can generate a space potential, equipotential a plot like what you see here. And then what you're looking for is what are the regions where the voltage, the space potential is less than 12 kV, where are the areas where it's between 12 and 25, and where are the areas where it's above 25. From that, you can pick your attachment points. So in this example that I've given here, you would say that this area and this area would be safe for a standard jacket. This kind of green rectangle that you see here or on the other side would be safe for a tracking resistant jacket. So let's actually do it. I've called up our program and let's see, we're doing okay on time. I've saved the this analysis. So here we have 5 cables. We're going to work in US units. You could name the project whatever you want. So this is this geometry that I just showed you. So the horizontal position minus 27 feet, which is what I showed you here. Minus 27 feet relative to the center of the line, 50 feet high relative to ground. 2750, 2 cables in the bundle, the conductor diameter 1.1 inches, the spacing of those cables in the bundle 18 inches. The phase to phase voltage is 345, which gives you a phase to ground voltage of 199. Here in our program, you can enter one and it will calculate the other. So if I enter 345 kV here, it calculates the phase to ground. If I enter the phase to ground over here, it calculates the line phase to phase voltage. So let's go back to 345 and then give the phase that it is. So A, B, C, I'm just assuming 0, 120, 240. So this is one conductor. The other conductor is at the center point of the cable, of the line rather. Here's cable number 2. 0, 50 feet high, 2, same values here. I just changed the phase. And then our C phase over here, we're at plus 27, 50 feet high, 2 cables, cable diameter, spacing, operating voltage again. And then those ground wires, 4 and 5, basic information here, works out to minus 13 and a half feet from the center of the line, 74 feet high, 1 cable, the diameter 0.364, spacing is 0, and then no voltage on those. You can include your ADSS position if you want. So let's say that I'm already was thinking I would put it horizontally. Oh, wait, actually, that's not going to work. It would be floating in the air. So I'm going to put it on one side of the the left side. And let's say I'm thinking I want it to be at 30 feet. Let's see how that works. You'll see this box here about environmental pollution. We'll come back and talk about that in a minute. So now you get this view of where the phase conductors are, the shield wire, and where I'm thinking of putting the ADSS. Then you hit calculate. And you get this plot. So I can see that my ADSS here is clearly in the track resistant jacket is required zone. If I tried to put it higher, I'm in the officially no-go zone. And if I can get away with only 20 feet, then I'm right on the edge, the ragged edge. is that really at 12 kV? Is that really okay? Well, actually, it tells you over here what it actually is. It's 10.8 kV. It's okay. So you could get away with a standard jacket there. I mentioned this environmental pollution. It talks about high pollution, so in or near an industrial area, on the coast, so within 15 miles of shore, low rainfall, don't you have less than 75 days of year with rain, or if you're in an area that's over insulated where your utility already increases insulation. All of these are very relative things. So it is possible that you could have a line that's 16 miles from the coast and it's close enough for you to have problems that we'll talk about in a minute. So, but if you click this box, really what you're going to get is this additional information, so about environmental pollution and what all of this means. So I'm going to leave it to you uh, to experiment with this later, try it, and then use it to impress your family and friends that you can do space potential analysis. So anyway, to keep going then. So let's see, we need to pick up our presentation. Things I didn't notice is that you do have the ability to save files. Of course, I guess you saw me open one, and then you can open it, and then you can change values like I did and experiment and have fun. And as I mentioned, impress your friends and family. You can also generate what we call a project code, and that will allow you to share what you've done with a colleague or, again, friends and family. Friends and family too. So to use the tool, there's no cost for it. There is, you do register your email address, but we don't do anything with email addresses, so you won't get junk from other people or anything. So I did promise that I would talk about microsparking, and I want to talk about that now. So the term is used kind of ambiguously. It could mean one of, I'm going to use it as a catch-all for two specific issues. One is tracking because a jacket is simply in too high of an electric field, right? So I've given you the limits to use, but somebody who doesn't do their space potential analysis and puts a standard jacket in a 20 kV field, they're going to have this microsparking problem and the cable's going to fail. And I showed you the tracking damage in a previous picture. The other term or way of using microsparking is when you've used a tracking resistant jacket, but it's in a high contamination area that doesn't have a good natural wet dry cycle. So what's going on there is that the pollution accumulates because of poor natural washing. And then you just get a little bit of moisture that leads to the tracking, and it's exceeding the jacket's ability to resist the tracking. So the problem with this is, okay, high contamination, what's high, and what is good natural wet dry cycle? And I don't have specific guidelines that I can give you. I know there are people out there, they will say, well, the pollution needs to be X number of something per square foot or something like that. There are people that talk like that, but in the real world, how would you know how much pollution is going to accumulate on your cable? And my answer is, I bet you don't know. And I bet you don't have any real way of knowing. So I think it's a very experiential thing. But if you're designing a cable today and you don't want it to fail, well, then the stand-in that you have is to look at your utility's experience with insulators. Because if your utility has had problems with tracking on insulators and is then over insulating, so maybe on a 138 kV line, instead of using 138 kV worth of insulation, you're using 169 or more. Well, that's a clue to you that your tracking resistant cable potentially could still fail because of this microsparking. So basically what's going on is environmental conditions are overwhelming the jacket's ability to resist tracking. And in that case, you've got to look at something else. So if a cable is in too high of a field, is there nothing that you can do? Well, it turns out that the answer is yes. Whether it's this microsparking condition or you're in a situation where the space potential analysis tells you that the attachment point is above 25 kV. And the answer is yes. You can cheat Maxwell's equations by grading the field in the immediate vicinity of the structure. And you can do that using a grading bar, which is what you see in this picture, or a corona tube, which is what's in this picture. So what's going on here is this just a piece of angle iron that's been attached to the structure such that it extends beyond the tips of the ADSS armor rods. You see the ADSS, you can see the rods and you can barely see the corona coil here. Likewise on this side. So you've extended this bar beyond that. Remember, the metal is going to distort the field. And what it's effectively doing is lowering the intensity in the area where you would have a problem. And a corona tube is just another way of doing the same thing. This is actually a product by Preform Line Products. It works exactly the same way. This has actually been done. So BPA has installed thousands of miles of track resistant ADSS on 345 and 500 kV transmission lines, and they're not having tracking problems. So it's not something just theoretical or hypothetical. It actually works. It is a thing that you can do. And again, shout out to Monty because he's the one who came up with this idea in the first place, and he's the one who gave me these great pictures. So, and that's our presentation for today. And I'll open up for questions. You're awfully quiet. You can type questions into the chat, or I think Alexis can unmute you. Maybe you can unmute yourself and ask questions. You're awfully quiet. Okay, if we don't have any questions, either I did a great job or I did an absolutely lousy job. I'll let y'all decide of a monopole circuit to show. Let me see. Okay, now I have questions coming in. Okay, questions. Let's go. Do you have an example of a monopole circuit to show? Let's see what I can come up with there. So, a monopole circuit. I might actually have one. Aha, so these are some other things I was messing with here. Well, like a monopole, let's go back and look down here. So we're going to put things on a center line, but let's assume that our insulators are, say, 3 feet. And we'll assume that we've got a monopole with the circuits on the left side for no particular reason. So that would look something like this. And the height, let's say 6 feet between phases. So probably be more, but whatever. We'll live with this. 62, oops, 62. And let's say the shield wire though is right at on the structure, close enough. Let's leave it. I know, let's do this. We'll keep our double shield wire configuration, but we'll say that it's 6 inches off the structure. Close enough, it'll work. So now we've got, oops, I did something wrong. Yeah, I did. I forgot a minus there. So your, your sketch helps you make sure that you didn't make a mistake in your data entry. And then I wanted to put my ADSS cable, let's say again, minus. So that's a monopole. And now I'll get fields that look like this. Okay. And then there was a question, monopole, how can we consider pollution values according to NESC on your, and it kind of dropped out. So like I say, I don't trust the pollution analysis. I mean, I know in theory, I guess there's some kind of an instrument that you could get and go collect pollution data. I really think that the using your insulator experience, because utilities have got insulator experience that spans decades. So if you're over insulating, that's a flag to you to use extra care. And again, there's notes in here about environmental pollution. So, I'm not sure I can really say anything more productive on that particular topic today. So there is a question. Well, what about the what's the effect of the phase? Not really a lot. So let's say that we want to change up our phases here. You'll kind of have to remember what we have here. So this was A, B, C. Let's go change it to CBA. Not a big difference. The same basic shape and output. Okay. Now there might be some weird configuration out there, like a double circuit configuration that would definitely get you a different result. In fact, let's have some fun with that. So let's add 3 more conductors here, and let's put them on the opposite side of our structure. Yeah. And we could even have more fun if we wanted to by changing the operating voltage using something different. In fact, yeah, let's do that for fun. 230. Oops, went too far, 230. And we'll make this B and 3, and what did I say, 50 to 1.108, 18. Sorry for talking to myself. Okay, and so now we've got double circuits on a monopole, and let's calculate that. It looks like that. Note the distortion because the operating voltage I said here is 345 and it's 230 over here. Now I should get different results if I change this, change the phases on one side, and I do. So when I put the phases, I think I have it now, CBA, CBA, things add up. If I reverse the phases, I would expect some cancellation.